Howdy calculus students. Today's topic is the mean value theorem. The mean value theorem establishes a deep and important connection between instantaneous rates of change and average rates of change. As an example, consider this scenario. Suppose that you go on a long drive and your average speed on that drive was 50 miles per hour. The mean value theorem says that at some point along your trip, you must have been going exactly 50 miles per hour on the speedometer. Well, this seemingly innocuous and unimportant observation actually lies at the heart of several of the major theorems to come later, including the extreme value theorem and the fundamental theorem of calculus. So our job today is just to understand the mean value theorem and get a sense of how it works.
Hello, calculus students. Today's topic is the mean value theorem. The mean value theorem is mainly a theoretical underpinning of several of the major results that come a little later in this course. For example, it's very important in talking about where functions are increasing and decreasing. It's actually right at the core of proving the fundamental theorem of calculus. So the mean value theorem is very central to all the big results in this class. But from a practical standpoint, it's not really the kind of result or formula that you use every day in doing computations and solving real-world problems. But because it is so important to making some sense of what we're going to talk about later, we need to spend a little time thinking about it. Luckily, the mean value theorem itself is not really super technical or hard to understand, and we can talk about it in terms of a very down-to-earth and simple question here. Let's just suppose that starting from a resting position, you drive your car in a straight line for 2 hours, and you travel 140 miles. And I could ask you, hey, what was your average velocity on this trip? And you would not have a problem doing that. You'd say, well, it's just my total displacement divided by the elapsed time. So it would be 140 miles over the 2 hours that you were traveling. And so your average velocity would have been 70 miles per hour in that situation. Okay, but here's my question. Was there some point in time while you were driving when your speedometer, which you can think of as your instantaneous velocity or your the derivative. So was there some point in time when your speedometer read exactly 70 miles per hour? Well, let's think about that. Is it possible that you could have had an average speed of 70 miles per hour, yet somehow your speedometer never read 70 miles per hour? Well, if you think about that, you pretty quickly realize, no, that's impossible. You couldn't have stayed under 70 miles per hour the whole time. If you stayed under 70 miles per hour the whole time, there's no way your average velocity could have been 70 miles per hour, right? Similarly, you couldn't have stayed above 70 miles per hour the whole time, because in that case, your average speed would be above 70 miles per hour. So, since you started from rest, your speed was at some point 0 at the very beginning, and then you sped up, and you must have been going faster than 70 miles per hour for some amount of time to get the average up to 70, right? So because acceleration is a continuous process, you can't instantly accelerate from 0 to faster than 70 miles per hour. You pretty quickly realize, yes, you must have been going 70 miles per hour at some point. So I'm just going to write down here what that explanation was. So this idea that over an interval of time, your instantaneous velocity must have been exactly equal to your average velocity over the whole trip is exactly what the mean value theorem says you should have. So the mean value theorem says, here at the bottom, first of all, you have to assume that you have a continuous function on your interval, and you also have to have that the function is differentiable on the open interval a to b, because we're going to be talking about derivatives in this thing. But the mean value theorem is if you have that set up, continuous function on the closed interval and differentiable on the open interval, then there has to be some point in the middle in a to b where the average rate of change, that's what's on the left-hand side of this equation, the average rate of change over that whole interval must have been equal to the instantaneous rate of change in other words, the derivative, at some point c in the middle. So the average rate of change has to be equal to the instantaneous rate of change somewhere in the middle of the interval. And you can even see this geometrically. In blue, that graph is the function f of x. And that green dashed line, that's just the straight line between the endpoints. And if you look at the slope of that green line, it's f of b minus f of a over b minus a. It's that average rate of change. And what the mean value theorem is, it says that somewhere there's got to be a point in the middle between a and b where the slope of the tangent line equals the slope of that secant line in green. There would actually be a couple of different places. It looks like maybe somewhere about in here, I could draw a tangent line whose slope would be the same as that green line. In other words, the tangent line would be parallel to the green line. Even looks like there would be a second place somewhere over here. The mean value theorem doesn't say that you can't have more than one place where the derivative is equal to the average rate of change over the whole interval. It can happen in several places, but it guarantees that there will be at least one such c. Okay, so it seems kind of like a so what theorem, like, well, why would I care? Like I said, this is more of a theoretical underpinning of what we're going to be doing that comes, like big theorems that come next. Let's consider a specific example. So we've got the function f of x equals x cubed minus 2x squared, and we've got a closed interval 0 to 3. And we've got a couple of things I want to check here. First is, when I determine if the mean value theorem, I'm abbreviating MVT, mean value theorem, determine if the mean value theorem applies to this function on this interval. And then the second thing is, if it does apply, then we want to find any of those points C where the derivative is equal to the average rate of change over that entire interval. And on the right over there, I went ahead and took the liberty of graphing that function just so we can kind of see what's going on geometrically. So first, let's do the part A. What we mean by determine if the mean value theorem applies to f on 0 to 3 is to check, are the hypotheses of the mean value theorem satisfied? So if we scroll back to the mean value theorem, in yellow are the hypotheses. We got to have that the function is continuous on the closed interval a to b and it's differentiable on the open interval a to b. Well, let's look at what we got here. Well, the answer will be yes, and the reason is that our function f is a polynomial. And what do we know about polynomials? We know polynomials are continuous on the entire real number line. So in particular, f is continuous on this subset of the real number line, 0 to 3. And then secondly, we know f prime of x is 3x squared minus 4x, and that's a polynomial. So is defined for all x, in particular, all x in the interval, open interval 0 to 3. So what we just pointed out here is that our function is continuous on the closed interval 0 to 3, and f prime is defined on 0 to 3, so it's differentiable on 0 to 3. Okay, next, since we know the mean value theorem applies, we know that somewhere between 0 and 3, there's a place where the derivative is equal to the average rate of change. And so we're being asked to find that value. The mean value theorem doesn't tell you how to find it. It just tells you that there is such a value c where the derivative is equal to the average rate of change. So basically what we got to do is solve for c, this equation. F of 3 minus f of 0 over 3 minus 0 equals f prime of c. What is our function? F of x is x cubed minus 2x squared. So the equation over here becomes, let's see, f of 3 would be 27 minus 2 times 9 is 18 minus f of 0 is 0 over 3 minus 0. And we calculated f prime above there. So f prime of c would be 3c squared minus 4c. And so on the left-hand side there, 27 minus 18 is 9, then divided by 3, so that collapses down to 3. And we got 3c squared minus 4c. So I'm going to write that as 3c squared minus 4c minus 3 equals 0. I don't see any obvious way that that factors, so it looks like I may have to use the quadratic formula here to figure out what c is. So c will be 4 plus or minus the square root of 16 minus 4 times 3 times negative 3. So 4 times 9 will be plus 36 all over 2 times 8. That'll be divided by 6. So hopefully you remember the quadratic formula and how to use it. That's what I was just now doing. And then, this is 4 plus or minus the square root of 52 over 6. And we could simplify that by pulling a 2 out of the top. We'd get 2 plus or minus, let's see, if I factor 4 out inside that radical, 4 goes into 52 13 times, so square root of 13 over 3. So I'd like to get a decimal approximation of that. I'm going to punch that in the calculator real quick and see what happens. Okay, so after plugging those numbers into the calculator, I get, when I use the negative square root of 13, I get the negative 0.54, and when I use the positive square root of 13, I get the 1.9, rounded to 2 decimal places. However, the c that we're looking for it to happen in this interval 0 to 3, right? So I'm going to discard that negative root because it's not in the interval 0 to 3 where I'm interested in looking. I'll discard that root. And so then this is my answer right here, 1.9, or precisely it's 2 plus the square root of 13 over 3 would be the precise answer. And I want to see on that graph, can I see what's going on, what the significance of this c is? Well, 1.9 is about this point on the graph right here in red. And if I would graph the tangent line there, it'll look like this. And I want to compare that to the graph of the secant line between the endpoints at 0 and at 3. So let's see what that looks like. There in green is the secant line. Do you see at that particular point that we found, that 1.9, the slope of the tangent line is the same as the slope of the secant line that connects the endpoints of the curve on that interval in question, which is 0 to 3 here. So visually, it looks like our answer checks out. That's what we were expecting to happen, because those two things being equal right here, or just those two slopes being equal, right? The red one and the green one above. Okay? All right, so that's the mean value theorem. So here, like I told you, the mean value theorem is important as a theoretical underpinning for a lot of things to come. And right out of the gate, we have two very important consequences of the mean value theorem that without the mean value theorem, I don't know how you would establish them. It may be very difficult without the mean value theorem. The first thing is that if you got a function that's differentiable and you find out that the derivative is equal to 0 over an entire interval, then that means that that function really must have just been a constant function. Now we know that when you start with a constant function and you differentiate it, you're going to get 0. But this is saying that constants are the only functions that have that property, that when you differentiate them, you get 0. So if you get some crazy function and you differentiate it and the derivative comes out to be 0 over an entire interval, well, that crazy function that you were looking at was really just a constant in disguise. And that's a pretty important thing to know. Let me show you why this theorem is true. In other words, let me give you a little proof of this. So we want to start off by supposing that f prime of x exists on this open interval I, and f prime of x is equal to 0 for all x in I. That's the hypothesis of that. Now I want to show that f is a constant function. So how do you show a function as constant? Well, the way you show a function as constant is you show that it has the same value at all points on that interval. So to show f is constant, we're going to show that f of a is going to be equal to f of b for all a and b in I, and we'll assume that a is less than b. But if you pick any 2 points, a and b, you can decide one of them's less than the other and then plug them into the function. You're always going to get the same result. F of a is going to be equal to f of b. So that would tell you that the function is constant, because it's always giving back the same result. Okay, on this interval a to b, f is differentiable because, this interval a to b is a subset of I, and we've already supposed that the function f is differentiable on the entire interval I, and we know that differentiability implies continuity, so this tells me that f is continuous on a to b. And we certainly know f is differentiable on the open interval a to b. F was differentiable on the entire interval I, so it's certainly differentiable on this subinterval. The reason I'm pointing this out is that these are the hypotheses of the mean value theorem. That f be continuous on the closed interval, and that it be differentiable on the open interval. So that means that the mean value theorem applies to this function. So the mean value theorem applies to f. And so here's what we know. We know that f of b minus f of a over b minus a has to equal f prime of c for some c in the interval a to b. But what do we know f prime of c is equal to by hypothesis? Well, our hypothesis was that the derivative was equal to 0 for every x in that interval I. So on the right-hand side of this thing here, this is just 0. And then you could take that equation and multiply through by b minus a, and you get f of b minus f of a equals 0. And then you can add f of a to both sides, and you got f of b equals f of a. So that means that that's what we were out to show, right? That no matter what we plug into the function, we always get the same result. And so we started off by just taking two arbitrary points, a and b, in the interval, and we showed that f of a has to equal f of b, so we get a constant function. This might be another so what theorem to you, but I think that I know for a fact that it's important for a lot of things that you do later in second calculus, but I think I can come up with a practical example here where you might go, okay, maybe that is useful for something. Look at this function here, cosine 2x minus 1 plus 2 sine squared of x. I'm going to compute the derivative of it. F prime of x is, derivative of cosine of 2x would be negative sine. That's the derivative of the cosine function of 2x. But then I got to multiply times the derivative of the inside function, which is 2. Then to differentiate the minus 1, I get 0. The derivative of 2 sine squared would be 4. Bring the 2 down on the sine, you get sine to the 1 of x. Then you got to multiply times the derivative of the inside function, which is cosine. And then let me simplify it just a little bit here. So this is just negative 2 sine of 2x plus 4 sine x cosine x. But hold on a second. I seem to remember from trigonometry class that sine of 2x, there's an identity for that. In fact, I remember that sine of 2x is equal to 2 times sine x cosine x. So this is negative 2 times 2 sine x cosine x. And then I can see right away that this is just equal to 0. So the derivative of that function that I started off up there with is identically 0. For every x in the world, the derivative is equal to 0. So this tells me by using the previous result, what was the number on it there? Theorem 4.5 tells me that f of x is constant. In fact, I kind of already knew that. I designed this problem to be that way on purpose. So you may get a function that you don't recognize as being constant because it has variables in it and it just doesn't look constant. But actually, I know for a fact, I know that cosine of 2x, there's an identity for that. Cosine of 2x actually equals 1 minus 2 sine squared of x. It's called the double angle identity. And so you can see that I should have been expecting that this function is just actually equal to 0, right? So of course it's a constant, but when we calculated a derivative, we detected that. Yeah, it's not that unusual to have some algebraic expression that doesn't look like a constant that actually turns out to be a constant. And so you can pick this up sometimes by calculating the derivative, and it ends up being 0. And the next theorem is closely related to the previous theorem. It just says that when you have two functions that have the same derivative, then those two functions can't be very much different. So if your functions have the same derivative, then it doesn't mean that the two functions are exactly the same, but they're going to have to be within a constant of one another. Like the difference between them has to be a constant. Like, for example, just up here in the margin, like if f of x is x squared and g of x is x squared plus 1, we know that both of those functions have the same derivative, right? F prime of x equals g prime of x equals 2x. So we knew already that if the two functions, the only difference between them is just a constant, then they'll have the same derivative. But what this thing is telling us is that it goes in reverse the other way. That if you know that the two functions have the same derivative, then they must have only differed by a constant. That's not obvious. The converse is obvious. If the difference between the two functions is a constant, then the two functions' derivatives have to be equal. That's clear, just because when you differentiate that constant, you get 0. But knowing that two functions' derivatives are equal and having that imply that the two functions only differ by a constant is not obvious. But it falls out from the previous theorem pretty easily. Let me show you why this is true. So, suppose f prime of x equals g prime of x on this interval I. So let's let h of x equal f of x minus g of x. And then let's compute the derivative of h prime of x. Well, we know both f and g there are differentiable because, well, their derivatives are equal to each other, so that must mean they're differentiable. So I can differentiate h, and it's just f prime of x minus g prime of x. But we just said that f prime and g prime are equal, so this must actually equal 0. Now, since h prime of x is equal to 0, the previous theorem tells us something about when the derivative is equal to 0 on an entire interval. Theorem 4.25 implies h of x is constant. So h of x is equal to some constant c. For some constant c, that is, remember h of x is just f of x minus g of x, right? So f of x minus g of x is equal to some constant, which was what we wanted to establish. Okay, so in this next example, we can see how to apply the previous theorem in a way that actually is kind of useful. It actually ends up providing an identity. So what we're going to actually show is that these two functions, f and g, are equal to one another. But it's not clear off the top of your head why. I think we could probably do some trigonometry to show that they're equal. But let's use this corollary, this theorem 4.6. If we can show that those two functions have the same derivative, then we'll know that they differ by at most a constant. Then we can show that that constant equals 0. So let's jump in by calculating some derivatives here. So what is the derivative of f prime? Well, remember the derivative of secant inverse of x is 1 over absolute x times the square root of x squared minus 1. And we can differentiate g. The derivative of cosine inverse is negative 1 over the square root of whatever's on the inside squared. And then you got to multiply times the derivative of the inside function. The inside function is 1 over x, and so you can think of that as x to the negative 1. And when you differentiate that, you get negative 1 over x squared. G prime of x is, so I cancel those negatives, and I can write it like this, 1 over, put the x squared in front of that radical in the denominator. And inside that radical, I've got 1 over 1 minus x squared. I'm going to write that as x squared minus 1 over x squared by getting a common denominator inside that radical. And I can take that square root of x out. A property you want to remember is the square root of x squared is equal to absolute value of x. So when I pull that x squared out of the radical in the denominator there, it becomes 1 over x squared over absolute value of x times the square root of x squared minus 1. And then x squared over absolute value of x, you can convince yourself is the same thing as absolute value of x. So this ends up being 1 over absolute value of x times the square root of x squared minus 1. So we see f prime of x is equal to g prime of x whenever x is not equal to 0. So theorem 4.6 tells us that f of x minus g of x is a constant, i.e. secant inverse of x minus cosine inverse of 1 over x is equal to a constant. Now, I know some specific values. For example, if I set x equals 1, if I plug in x equals 1, I know secant inverse of 1 minus cosine inverse, that would be 1 over 1, which is just 1. Well, secant inverse is, at what angle is the secant equal to 1? Well, cosine is equal to 1 at 0, and so is secant. So this is just 0 minus 0. So that tells me that my constant c is equal to 0, and then from there I can conclude that secant inverse of x is equal to cosine inverse of 1 over x. And you can think of that as a new kind of identity for inverse trig functions. That's actually kind of cool. And I was able to get it by knowing facts about derivatives. I like it. Main theme of this section, though, was we looked at the mean value theorem, and we played around with what it means in terms of average rate of change equals instantaneous rate of change. But we understand that really the results we found in this section are underpinnings for things that are to come that will be more useful for doing things like, solving real-world problems. And I'll stop there, and we'll talk to you later. Bye now.